Hello grade 12s, this is physical science and my name is Gillian. We are going to tackle that big section, chemical equilibrium. Now, if we look at the big ideas, they're just a few and we can have a look at them individually and get to grips with this massive section. So let's have a look at an overview and see what we already know. So my overview in the middle, you can see here, we've got chemical equilibrium. Now, understanding and definitions. So this part here, understanding and definitions, we know a couple of definitions, but the definition for chemical equilibrium, you need to know off by heart. Those keywords are the ones that are going to give you the marks. So open system, you know about an open system. A reaction that happens in an open system can never be or never reach equilibrium because the reversible reaction can never happen. If our products are escaping, then we can't have, our system can't reach an equilibrium, a chemical equilibrium. It needs to be closed. So what does that mean? Either there's a top on the vessel and so the product can't escape, or it happens within a solution. So there is naturally a closing on that, that vessel because it is within solution and no gas is being made in order to escape. So for chemical equilibrium to happen, first of all, we have to have a reversible reaction. If it's not reversible, it's not going to happen. The reaction will continue to its end and it will not reverse back. So we have to have a reversible reaction. It has to be within a closed system. So we will have a look at that definition in words in a moment. The other things that we need to know about chemical equilibrium are the factors that affect that equilibrium. We're going to dive into three: concentration, temperature, and pressure. You know about pressure, Boyle's law. You know that if we push a gas closer together so that the volume decreases, so we're talking about gases only, the volume decreases, we're forcing those particles of gas together, the pressure is going to go up, it's going to increase because all those particles have nowhere to go, they're bumping into each other and against the side of the container, and so the pressure increases. So Boyle's law is if you decrease the volume, the pressure is going to increase. So it's an inversely proportional relationship and pressure applies to gas only. Temperature is an interesting one, and we're going to have a look at temperature in relation to graphs and how we can read it off the graph and can we pick up the patterns that are happening within the graph. Concentration is the number of moles per volume. So we know this equation, which is concentration equals number of moles over volume. For pressure, we know that the volume is inversely proportional to the pressure and vice versa. Graphs, there are two that we're going to look at in a little bit of detail. So the first one is the concentration versus time graph. And you've seen this in rates, so it's nothing new. So if we've got a product and we're checking out its concentration, it is going to do this, a curved line. So the concentration of the product starts at 0, and as the reaction progresses, it then increases. If we're looking at the concentration of a reactant, we see that the reactant starts really high. There's a lot of reactant in that vessel, and as it reacts, it decreases. The same applies for rate versus time. So the rate of the reaction is going to be shown on the graph, and we've got two reactions we're dealing with here in chemical equilibrium. We're dealing with a forward reaction and a reverse reaction, and so that is why on the graph you will see there will be two lines, a forward reaction and a reverse reaction. And so we're going to have a look at that in detail. Calculations Calculations are usually involving the equilibrium constant. The equilibrium constant is denoted by Kc, and we have to write a very specific expression for the equilibrium constant that is particular for a reaction. It's not a general reaction, a general equation. It has to be very specifically set out for that reaction that you are being asked about or that you have been given. So we're going to have a look at Kc and the expression that we write for a specific reaction. Then we have this interesting man, Le Chatelier, and his principle. And Le Chatelier is talking about what happens when a system has already reached chemical equilibrium and there's a disturbance, a knock on the door, a shake-up. How is that equilibrium system going to respond in order to counteract that disturbance? Let's continue now to our first big idea about how do we write the definition for dynamic equilibrium. So dynamic equilibrium is telling us that this equilibrium is moving all the time. We might look at the vessel and think, this isn't moving, there's no reaction happening here, but actually something is. There is a forward reaction and there is a reverse reaction, and that is why it is called dynamic. It is moving. It is reached when the rate, so we're talking about rate again, and rate is time. It's how fast something is happening. So it is per unit time. The rate of the forward reaction equals the rate of the reverse reaction. This has to be a reversible reaction, as we've spoken about, so you have to put in that word. It is a reversible reaction. It doesn't happen for a reaction that goes to completion and stops. And then it has to be in a closed system. Learn that. It is really important. How do we calculate Kc? This expression, how do we write it? How do we calculate it? This is our second idea. Now, the equilibrium constant, there are a couple of conditions that we have to remember about it. It only applies for something which is in the gas form and something which is in the aqueous form. It does not apply for something which is in solid or something that is in the liquid phase. And the reason why is because Kc is revolving around concentration. Concentration at equilibrium. Once the system has reached equilibrium, what is the concentration of our products and our reactants? So with a solid and with a liquid, the concentration is always 1. And with 1 times anything is going to be anything. So we disregard something which is in a solid form or something which is in a liquid form. Now, Kc for a chemical equation that has reached equilibrium will be the same unless the temperature of the system is changed. So Kc only changes with temperature. So it changes with temperature. So if temperature is increased or temperature is decreased, then the Kc value is going to change. Otherwise, nothing will make that Kc value change. It is constant. Right, here we have the symbols that we're going to use for concentration. They're square brackets. Concentration, we know, is the number of moles divided by the volume. For a particular reaction, we are going to express the Kc value as follows. I've given you an example here. It is the formation of ammonia gas. You can see that nitrogen gas is used, so is hydrogen gas as the reactant. It produces ammonia gas. It is a reversible reaction. So ammonia gas then breaks down to form the hydrogen and the nitrogen gas. We can use all three of those substances because they are all in gas form. So what is Kc really? The equilibrium constant is looking at the ratio, the comparison between the concentration of the product and the concentration of the reactant, of the forward reaction. So Kc here is the symbol, and the concentration of the product of the forward reaction is NH3. Now you will see there is an exponent 2 over there, and that correlates with the coefficient of the ammonia gas. So this reaction, before we can write the Kc, this reaction has to be balanced so that we can maintain the conservation of atoms. So it's a balanced reaction equation, and the 2, that is the coefficient of ammonia, is then placed as an exponent. So we square the concentration of ammonia gas. We divide that by the concentration of nitrogen gas and the concentration of hydrogen gas. It's times together. And look here, we cube the concentration of hydrogen gas. Why? Because it has got a coefficient of 3. So when you are writing this, you need to be extremely particular about the expression that you're writing. It has to be specific for the balanced equation of the reaction that has been given to you. Now, if Kc is greater than 1, it means that the concentration of the product of the forward reaction is high. And so we can figure out where this equilibrium is sitting. We can figure out at equilibrium there is a large concentration of product formed. If Kc has a value which is smaller than 1, it's less than 1, then we know that this concentration of product for the forward reaction is low. We get a low value of Kc. That means that the value of the concentration of the product is low. So the Kc value is not just a number. It tells us a lot about where the equilibrium sits. Right, grade 12s, it's time for a brain break. We'll see you later. Welcome back, grade 12s. We have been busy looking at Kc, the equilibrium constant, and now we need to check out how are we going to use this in a problem, in a calculation. So you might have heard of this. It's the Rice table, which stands for ratio. R is ratio, I is initial mole concentration, or number of moles. C is the change in the moles, and E is the equilibrium, what's happening at equilibrium. So we use this as a tracking for ourselves. It's to plan out how the number of moles of a substance changes initially through the reaction and then finally at equilibrium what is happening. So if you look at my screen here, you'll see right at the bottom, it says here concentration at equilibrium. Now, we've already looked at that equation. Concentration is equal to number of moles over volume, and concentration at equilibrium is where we get our Kc value from. So that is where Kc fits in. We're looking at the concentration of the substances when they have reached equilibrium. I have given you in this table a phantom equation. You can see there it's A, B, and C. My reactants are A gas and B gas, and my product is C gas. I have a double arrow telling me that it is a reversible reaction, and it is balanced. You can see I have 2 in front of the A. So that balanced reaction is going to give me the ratio at which the reactants react to form the product, and the other way around, the way that the product then reacts to form the reactant for the reversible reaction. Initially, at the very start of the reaction, I will have no product. There we go, it is 0. There's no product, there are no moles formed. So, I will only have moles of A and B, my reactants, and I'm giving you those. So I'm saying initially at the start of the reaction, I have 12 moles of A, 15 moles of A, and I've got 12 moles of B. Now, let me tell you, this I'm telling you, I'm giving it to you, that in this reaction, there is a change in the product, and the change is 4 mole. So that means that 4 mole of C is formed during the reaction, and so at equilibrium, I will have 4 mole of C. So now I'm going to work back. How does that then impact the reactants and how they are being used up? So the change in mole, I need to use the ratio. So if 4 moles of C are formed, the ratio is 1 to 1, so 4 mole of B will be used up. We put a minus there because it's used up. For the ratio of A to C, you can see that's going to be 2 is to 1. So if 4 mole of C is formed, then 8 mole of A is going to be used up. So you can see there that we're getting further and further into our calculation. So at equilibrium, what will the number of mole be for each of these substances? So we're going to subtract, because the change in mole is what is used up by A, or how A is being used up. So 15 minus 8 is going to be 7, so there'll be 7 mole. 12 minus 4 is 8, and so they're going to be 8 mole of B, and of course we have then 4 mole of C that is formed. Now, the concentration at equilibrium, according to this equation, is number of mole divided by the volume. So if we say that the volume is a decimeter, then we can divide each one of these by the number 1 decimeter, and so we'll get an answer of 7 decimeters, 7 mole per decimeter. I'm just going to put that in there, that's the concentration. This one would be 8, so 8 mole per decimeter cubed, and then this one would be 4 mole per decimeter cubed. Okay, so this is how we use the Rice table. It is very helpful in formulating what is happening with the number of moles of substances, the reactants and the products, and we can then figure out the number of moles at equilibrium, and from there we can calculate the concentration. And once we know the concentration, which is mole per decimeter cubed, we can then calculate Kc. Let's move on to our third big idea, which is Le Chatelier. Now, Le Chatelier's principle, you need to know off by heart as well. So when the equilibrium in a closed system is disturbed, that big word, disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. You need to know that off by heart. So how do we apply Le Chatelier? There are 2 ways we can be asked Le Chatelier. The one is we are told what the disturbance is, and then we have to say in words how we're going to answer these questions. In words, this is what we have to do. We need to identify the distress or the stress. We need to write it in words. We need to state how the system is going to respond to that distress. We need to state which reaction is favored, and then we have to say what effect is the new equilibrium going to have. The second way we can be asked Le Chatelier is by looking at the graph. So there are those 2 graphs. the rate versus time graph and the concentration versus time graph, and we can see a disturbance in those graphs, and we'll need to be able to interpret them and then write in words what is happening in that particular reaction. So let's have a look at this concentration versus time. It is a well-known graph. You can have a look at it. This is for the same reaction of making ammonia. It is reversible. Please take note of this change in enthalpy. It is important in temperature, but you can see that the concentration is decreasing of the reactants there, nitrogen and hydrogen, and it is increasing for the ammonia until equilibrium is reached. And when that is reached, when the rate of the forward reaction is the same as the rate of the reverse reaction, the lines are parallel to the x-axis. So all those lines are straight lines, they're horizontal lines, and that is when we know that equilibrium has been reached. So if we start adding a disturbance, so we mess around with the concentration, we can either increase the concentration or we can decrease the concentration. What is it going to look like on this graph? So if you look at the concentration versus time graph, you can see that equilibrium has already been reached. You can see that those lines are horizontal and parallel to the x-axis. Now what happens is one of those components, you can see the hydrogen there is in the yellow, suddenly peaks. Look at that. It goes straight up. It is a vertical line. Something has happened to disturb the equilibrium. And for this, it's going to be this particular line that you see is telling you that the concentration of the hydrogen has changed and it has been increased. So when we write out Le Chatelier, his principle, we write out what's going to happen. We're going to follow those four things. So what is the stress or the distress? Well, there has been an increase in hydrogen concentration. You need to write it. An increase in hydrogen concentration. What is the response? So what is going to happen to the system to try and alleviate that stress? Well, the system's going to try and decrease now that increase in hydrogen. And so what's it going to do? It is going to try and take away that increased concentration. And so the system will react to decrease the hydrogen concentration. There we go. We're going to write it in words. Which reaction is favored then? Well, it has to be the forward reaction, because the forward reaction is the one that's going to take away the hydrogen it's been used up to form something new. So the forward reaction is favored. What is the effect then? Well, there's going to be an increase in the concentration of ammonia gas and a decrease in the concentration of nitrogen gas. I think we have a few more minutes to have a look at this. When we look at the rate versus time graph, you can see over here, that is where equilibrium has been reached prior to the disturbance. Now there's a disturbance. There are two lines here, one telling you that we have a forward reaction and one telling you that we have a reverse reaction. So you can see here there's a vertical line. It is telling you the disturbance is in the forward reaction. Somehow the rate of the forward reaction has increased dramatically. And so you can read from that that there has been a disturbance in the concentration of either hydrogen or nitrogen in this case, we don't know which one, and the equilibrium has shifted to alleviate that distress and has favored the forward reaction. Once again, you see here the lines are parallel, and so equilibrium, a new equilibrium has been reached. I want to speak quickly about temperature because temperature is quite interesting. Temperature is going to affect both the forward and the reverse reaction. However, there is going to be one reaction which is favored because of the change in enthalpy. So when we try and write about Le Chatelier and the disturbance of temperature, we need to look at the reaction that's given to us and the change in enthalpy. We know that if delta H is a positive value, then the forward reaction is endothermic. If delta H is a negative value, then the forward reaction is an exothermic reaction. So exothermic is releasing energy, endothermic is taking in energy. So if we have an increase in temperature, the reaction which is going to remove that increase in temperature is going to be favored. So for this reaction, the forward reaction is exothermic. Let's say we increase the temperature, it's increased. The reaction that's going to use up the heat is going to be favored, and so that is going to be the reverse reaction. The reverse reaction is endothermic. That's going to absorb the heat, the increase in temperature, the energy, and so the reverse reaction is going to be favored. In terms of Le Chatelier, this is how we write it. Stress, what is the stress? There's an increase in the temperature. What is the response? The system is going to respond to decrease the temperature increase. So which one is favored? The endothermic reaction is going to be favored, and in this case it is the reverse reaction. What is the effect? Well, the ammonia gas concentration is going to decrease, but the product concentration is going to increase. Grade 12s, I'm hoping to see you for the consolidation lesson. You have to come. We're going to be discussing calculations. For now, it's a day.